Our next speaker would be Griffin Higgins. So Griffin is going. His topic is CIC statically generated graphs for malware analysis. Griffin Higgins is a PhD student in computer science at the University of New Brunswick and the Cybersecurity Software Developer at the Canadian Institute for Cybersecurity. He completed his Bachelor's of Science, Bachelor's of Arts in Sociology, and Master's of Applied Cybersecurity, plus research intensive cyber knowledge studies from UNB in the year 2020, 2021, and 2022 respectively. His research interests include the cyber threat intelligence and the privacy preserving deep learning and adversarial machine learning. Although it's not a part of his introduction, but I must mention the hackathon that I mentioned. Griffin is the person responsible, behind the hackathon that we organize for high school students every year. With this, I welcome, Griffin to this segment. Griffin, like I said to the previous speakers, the stage is all yours.
Awesome. Thank you so much for the warm introduction, Sumit. And yeah, we always love putting on hackathons and different events for students. So I hope everyone can see my screen and hear me well. Just give me a little shout if not. But yeah, so today we're going to be talking about CIC statically generated graphs for malware analysis. It's May 9th, so let's jump into it. As Sumit mentioned, I'm a PhD student in computer science here at UNB. I'm also a cybersecurity software developer here at CIC, and I have a background in computer science, sociology, and cybersecurity as well. So on the agenda, we just did the introduction, and after this, we're going to look at some background. There's a lot of different pieces to put together to understand what this data set is. It's quite a unique data set. So today, instead of focusing on like the nitty-gritty features and stuff, I just want everybody to come away understanding what this is and how it can be applied almost at like an undergraduate level, if that's kind of the minimum bar. After that, we'll cover the data set and answer a lot of questions about it. And then finally, we'll take some Q&A at the end. And I'm also going to start my timer. Perfect. So I'm going to hit you with this right up front. I always like to start with a bit of a bang because this is actually what we're going to be moving towards understanding. And as you may have guessed, it is kind of scary looking, and it's because it's malware. And in this case, it's an explained piece of malware as a graph. We're going to talk a little bit about what that is, but just to give you like a precursor idea before we get there. So, but first, before we talk about this, we need to talk about a couple other things. And principally, what should you know before you start to dive into this data set? So we're going to cover a little bit about malware, a little bit about malware detection, static analysis, graphs, program graphs, and then graph learning, and how they all relate to our data set. We're just going to talk pretty plainly about them right now, just so that people can get an idea about what this data set is. So in terms of malware, what is malware? They're programs designed or misused with specific malicious intent to cause harm to other people or otherwise violate CIA. And there's various different kinds of malware families. We might know some of the more common ones like ransomware, worms, etc. So that's a little bit on malware. In terms of malware detection, very simply, I give you a binary program or a program, and you tell me if it's malicious or benign. So that's pretty simple, but there is a little bit of a bonus in terms of if you do make this kind of prediction, can you also tell me what parts of this program lead you to believe that prediction strongly? So that's kind of another part. After this, we're going to talk a little bit about static analysis. So again, just very quick fire things. I give you a binary program and I want you to tell me what it does, but the catch is that you can't actually execute it. You can only really look at the code and try and make guesses about it that way. In contrast to something we might say is dynamic analysis, where we actually run the program in order to talk about it. Another thing we're going to talk about a lot today are graphs. So this is kind of a strange word for some people if you're not in computer science, but it's the same thing as what most people would know otherwise as a network. And networks are just a data structure, and they have a set of nodes that are sometimes called vertices as well as edges. And these edges between nodes, the things that connect them, they can be directed, i.e. like you can go from A to B, but you can't go from B to A, or they can be undirected in that like you can go from A to B or B to A if you have two nodes. There's many different kinds of graphs. Some of them are called multi-graphs, where you might have multiple edges between the same two nodes. And graphs can also have attributes. So we might talk about the graph as a whole. It might be malicious or benign. We might also talk about a node, and we might look inside of it and talk about its instructions, right? Or we might look at an edge and we might assign it a value in terms of how much it contributes to a final prediction of something being malicious or benign. So these are all just kind of things related to graphs that we might extend to programs later. And this is a good segue because the next part is on program graphs. And essentially here, I give you a binary program and I want you to transform it into some kind of graph. And typically there's two ways to do this. One is through control flow graphs, where essentially we take sequences of non-branching assembly instructions and we stick them into one node. And then whenever the code branches off, we create an edge to that other node and then have all of its assembly instructions. And we keep going until we've exhausted the whole program. Similarly, we can also consider function call graphs. Except in this case, we're not considering sequences of non-branching instructions. We're just considering the functions that you and I might classically know if we're doing some programming. So, okay, this is a little bit more on program graphs. We're kind of chugging along all these different pieces of our data set. What else are we going to talk about? One of these things is going to be graph learning. I know some of my colleagues have and are going to be talking about this a little bit more. But in our work, we apply deep learning techniques to graphs via graph neural networks. And the reason that we do this is so that we can start to talk about the behavior of malicious programs rather than just matching signatures. And if anyone wants to ask me a really good question at the end, ask me like what the benefit of doing this would be. So I wanted to also include this short little video just talking about graph learning. And here we start off with this network and all these nodes. We might recognize them as people. And essentially, we're going to give each node a message. And what we're going to do is we're going to share that message with all of our neighbors. And then after we're done, we're going to take that message and then we're going to start sharing it out with our message again. And we're going to do this over and over and over and over again. So we might ask, what is the purpose of doing this? The purpose of doing this is so that we can start to talk about each node and its little neighborhood around each node. And then hopefully after we do this kind of message passing enough times, maybe even millions of times, we can get a good representation for what the graph actually is at a structural level. And we will be able to represent that with a sequence of numbers that are typically called an embedding. And we're going to use this embedding to make predictions about whether or not our graphs are actually going to be malicious or benign. So that's just a very crash course thing in graph learning, just so that we can get a very rough idea. There's a lot more to it, but again, just getting a rough idea for what this data set could be used for and the different parts of it. So again, there are different kinds of tasks in graph learning. The one we're obviously most concerned with in our work is the graph level tasks. So if I give you a program, can you tell me if it's malicious or benign? But there are other kinds of tasks. We might talk about node level tasks that are kind of in orange here. So predicting what kind of class a given node might be. We can also talk about edge level tasks. So predicting if an edge exists or if there's a certain kind of value on an edge. It can extend far beyond just graphs and graph classification itself. So, okay, great. We've covered all of the very high level things related to our data set, and now we're ready to jump into some of the details about it. So first question you might have is why make this and how did this come about? So we previously were working on an industry project, and we still are, and it focused on graph learning and using graph learning for malware detection, unsurprisingly. So in this work, explainable malware detection through integrated graph reduction and learning techniques, together with my colleagues, we basically set out on this task. And we found something very interesting, and that was that the graphs that we made from these programs, these control flow graphs and these function call graphs, tended to be quite large. So the majority of our work was spent trying to figure out how do we actually reduce or collapse the size of these graphs. So that's why it's talking a lot about graph reduction. But apart from this, we did all this work and we looked at the various stages of this pipeline. And we thought, okay, let's actually make this available for other researchers so they don't have to set up this big pipeline or get all these malware samples and convert them to graphs and do all this hard work. Let's just give it to them so that they can get to work. So that's the why, but this is the how. So I was always thinking earlier about the old Discovery Channel, how it's made. We're going to start from the very beginning and then go all the way down to how we actually get explanations from the graphs. So starting out, we obviously need some malicious binaries. If we remember earlier, this task of if something is malicious or not, we need a binary to start with. So in our work, we consider 3 different data sets. We consider the DikeDataset, the PE for machine learning malware detection dataset, as well as the BODMAS dataset. And some of these data sets are open, so you can just go download them yourself, and they contain both malicious and benign samples. And some of them are closed, so you basically have to request access, and then they might actually give you the binaries. Also in our work, we're just considering only PE files, and essentially we're focusing on the x86 architecture. So after this initial stage of getting all these data sets and kind of filtering them down a little bit to get exact samples that we want, we can begin to move forward with actually creating the graphs from these binary samples. So we do that in many ways. This is also a good question if someone wants to ask it later about the challenges that exist here. But again, I want to be in time, so I'm going to skip it. So we take these binary samples and we can pass them through various tools, one of which is called angr. And this is the thing that will actually generate our control flow graphs and function call graphs for us. And it will give them back to us as a network X object. And one of the really interesting things I think about this data set is that this can be helpful for both malware analysts and graph learning specialists. So if you're really focusing on malware analysis, you can use these graphs because they are the things that are actually going to contain the raw features. So if you go and you open up one of the graphs and you go and you open up one of the nodes, there's like a small treasure trove of information in there. We couldn't even explore all of it, but it's there for researchers if they want to. Another important point is that these graphs here are not actually used for training or testing. They are just attribute graphs that we actually use to make the next segment, which are going to be called the embedding graphs. So after we have these attribute graphs, the thing I just talked about, we're going to make the embedding graphs, and we're going to take all of these nodes and the node features. So basically, when we think to the video earlier, how each person in this network had some information above them, like that little message, that's actually just a list of numbers. And what we're going to do is we're going to use this to actually pass the messages around. But before we begin, we actually have to make this message. So we look at all the feature nodes for each node to make that list of numbers. A little rambly, but I hope that got through. After this, we can take it and give it to another program called PyTorch Geometric. And these are actually the graphs that we will use for training and testing all of our various graph learning models. And importantly here, these are the graphs that you're going to really care about if you're into graph learning, or maybe if you're trying to merge these two fields of malware detection and graph learning. So they have all the embeddings for each node, as well as the positions of like where they occur, because maybe you want to prune off some of the nodes, but also have references back to where they were in the original graph. So that's a little bit more about the different stages of this pipeline. And as we keep going through, we can start to look at the graph pruning algorithms. So we don't include these samples in our data set, but they're free. If anyone wants to apply the same algorithms, they're welcome to do so. And then at the very end, we might actually try and think about the explanations for these graphs. So after we pass them through our different models and predictions are made about them, what are the nodes, if we recall back to the malware detection part, it was that kind of that bonus. What are the nodes or the edges that actually contribute to a given prediction? And can those be used in the future? So again, after we have all of the data set, we're kind of working through how this is made. We can take a look at the different machine learning models or graph learning models, and we can do inference on them after they're trained, so we can answer those initial questions related to malware detection. We can also look at the explanation, the thing we just talked about. So that's where it all kind of fits into this little ecosystem that our data set is extracted from. So you might also ask, what's actually in CIC? Like if I go and I download it right now, what is actually there? So we give you the following things. We give you the attribute graphs that we talked about. We give you the embedding graphs that we talked about. And then we also give you the explained graphs. So if you take the same sample for each one of these, it will have the same structure. Like if you looked at a plot of it or you just visualized it, it would be the exact same. But the features, the information in each of these is going to be slightly different. So, okay, you might actually also ask, what do these look like? We've been talking about these at a very abstract level for a little while. So these are two images of the function call graphs where we use the function name embedding technique, where we just take the name of a given function and we pass it through a sentence transformer, which gives us basically a list of numbers that we place over the node, very simply put. But here we can see the malicious is going to be on the left in red here, and then the benign sample is going to be on the right in blue. So we can kind of see that these look like quite dense graphs, but actually it gets much worse. Because once we go to the control flow graphs where we use the assembly embedding technique, we can see that the size of these graphs just explodes. So in the malicious case, there were a few samples, I think, that reached almost to 300,000 nodes each. And once you start to do anything at that level, your life becomes difficult. Even to generate the images you see now here, it took, I would say, like 8 to 12 hours for it to actually arrange the plotting coordinates for each one and then actually to render it. So you can imagine now why the graph reduction techniques would be important if you're going to do something like graph learning. So yeah, that's just a couple images of the graphs themselves. Very cool. And one of the last things we're going to talk about is where actually is CIC statically generated graphs 2024. So if you go to the Canadian Institute for Cybersecurity website, and this is the same for all of my colleagues that are here talking today, if you go to the datasets tab and then you kind of scroll down, you'll be brought right to all of our datasets. Eventually, if you click on one of them, you'll be brought to like the dataset description page. And then finally, if you scroll all the way down to the bottom, you'll see a little place to actually go and download. When you click that download button, you're actually going to be brought to like the server where all the data is hosted. And for our data set, you're going to see the following, where we're going to have essentially those 3 directories we talked about, which contain the attribute graphs. They're in the CFGs, FCGs, a little bit of a tongue twister, as well as the embedding graphs, and then finally the explained graphs. We also include like a zipped version of the data set because some, especially the embedding graphs, are quite large. They can reach almost 230 gigs. So one of the things we do is we make each and every one of the individual samples also available to download if you so choose, because maybe people don't have a couple hundred gigs just sitting around on their disk and they'd rather just have a couple samples. So yeah, that's a couple of our references for obviously the BODMAS dataset, the DikeDataset, and the PE for machine learning dataset. Thank you to all those people for the hard work in collecting those samples that enabled us to make the graphs in the first place, as well as thank you to all my colleagues for their hard work on our papers. So yeah, with that, I think we've covered the following things. What should you know to understand the CIC dataset? Why make the dataset? How is it made? What's actually in it, and where can I get it? So with that, I think we're wrapping up a little bit early, but maybe we can take a couple more questions if that's the case. Thank you so much.
Thanks, Griffin. That was I mean, certainly insightful, and it's always nice to show our viewers how they can access some of those data sets.
Yeah.
Let me just see if there are questions that
Sure.
we have in the chat section. It certainly seems we do have a few, so I'll go about and read the first one. So, what is the largest challenge related to using the static CFGs and FCGs?
Yeah, no, that's a wonderful question. So I think just the sheer size of these graphs, it can sometimes take upwards of hours or even days to get through a whole data set if it's unpruned, right? And another challenge is whenever you're working with graphs, sometimes you should get a little scared because one of the things that we're obviously concerned about in computer science is this notion of computational complexity, which just describes like how hard are the problems we face. And whenever we start talking about graphs, especially large graphs, you'll kind of see computer scientists start to sweat a little bit. So any way that we can to reduce the size of those graphs makes our life, in some cases, exponentially easier. So that's the main challenge, is just figuring out not only those algorithms, but what are fast pruning algorithms, what are efficient pruning algorithms, what are fast pruning algorithms. So that's a big one. And I would also suggest something we didn't know at the start of the project. We worked a lot with NetworkX, but towards the end of the project, one of my colleagues suggested a really good library. It's called iGraph in Python. It's really, really fast. So that would be my advice to anyone that might be taking a long time to run your programs, is try that library out.
Okay, okay. Thanks, Griffin. That was again very insightful for people who are looking to, further their research in this area. With this, we move on to the next question. What else could researchers do with CIC-SGG 2024?
Yeah, absolutely. So we kind of focused a lot on the graph classification, but again, there's so much more to it. You could take a look at each one of those sub data sets, if you will, separately, even though they reference the same graphs, because you can look at the explanations for given predictions and see what's going on with them in a little more depth. You could also take a look at the attributes. We didn't have time to look at all of them. There's tons and tons of features if people wanted to figure out how to make better graph embeddings for the nodes. That's obviously a really good direction. You can take a look more at trying out different models for graph learning, seeing if you can get better predictions, better accuracy. All those things are always great. And then the last thing would be maybe considering different kinds of tasks. So we were again focused on the graph level task, but maybe we can take a look at edge level tasks for predicting if there are going to be certain edges between nodes or not. Another interesting thing that we didn't get to was in the graphs, the positions of the graphs are given there, so you'll know which nodes might occur before other ones. So maybe you can also consider like the state transitions as a function of time, or the temporal nature, or temporal graph learning, I believe is what it's called, where you can see and make predictions about the graph as it evolves over time. So that might be like a fourth dimension to the graphs that people can maybe consider. Yeah, awesome question.
Interesting. Thanks, Griffin, for this. And the next question is kind of interesting one. Like your data sets, what is the industrial application of that?
Yeah, so obviously for malware detection, one of the drawbacks is that sometimes it can be a little bit slow because you're having to compete with signature-based detections, which are usually quite fast. But the drawback is that when we're looking at signatures or indicators of compromise, one of the big drawbacks is that they can be easily changed, right? Like if you have a hash of some kind of binary sample, which is just like its fingerprint or its signature, you might be able to change like just one bit, and then you'll have an entirely different signature that might be able to evade some kind of detection, right? But even though that's fast, that's a big flaw that we address through graph learning, right? Because at that point, you can actually start to talk about the behavior of the program or what exactly it's doing that makes it malicious, as opposed to, okay, I just have some hash in a database, match, go about my life. Even though that's a very good approach, it doesn't get all the way there.
Interesting. Thanks for elaborating that, Griffin. Our next question is with respect to the function name embedding. So can you talk a bit more about the function name embedding and assembly embedding techniques?
Yeah, no, so that's a really good question. For the function call graphs, we can only apply the function name embedding, obviously, because they're the only ones with functions that have names. But again, we take those names and we can pass them through sentence transformers that, again, all we're looking for is just some representation for each node to have a list of numbers so that we can pass all those messages around with our neighbors and get representation for the graph. That's kind of the main purpose. But you asked another really good question, which is on the assembly embedding. So this one's a little more in-depth and intricate. So in this case, where we're considering a control flow graph, each node, again, represents a sequence of non-branching instructions. They're also known as a basic block. And what we do in this case for this particular graph is we take each and every instruction in that node, in that sequence, and we embed that instruction. And at the very end, we sum them all together. So we'll actually have a representation for the instructions within each basic block that we then use as that message that we kind of pass around. So yeah, there's a little more technical detail to it, but at a high level, that's kind of what's going on for both of those embedding techniques.
Oh, interesting. Griffins, I think, let me just quickly scan through our chat section if there are any further questions.
Yeah, sure.
I think with this we come to the end of the Q&A session with you, which means thank you for your presentation, Griffins, and thank you for answering some of those questions.